You're walking down the street when a tennis ball comes flying toward your face. Your hand shoots up instinctively, catching it midair. In that split second, you just experienced one of the most fundamental concepts in all of physics: forces. But here's what's fascinating. That catch you just made involved not one, but multiple types of forces working simultaneously. Some you can see and feel, others you can't even detect, yet they're shaping every single moment of your existence right now. Today, we're diving deep into the world of forces, and I'm going to show you how everything from catching a tennis ball to the reason you're not floating off into space comes down to understanding two major categories of forces that govern our universe. By the end of this exploration, you'll see the hidden mechanics behind every push, pull, and interaction around you. And trust me, once you grasp this, you'll never look at a simple game of tennis the same way again. So let's start with that tennis ball scenario. When you catch it, your hand makes direct contact with the ball. The ball pushes against your palm pushes back against the ball. This is what physicists call a contact force. Physical touch between two objects. Think about it. When you stretch a spring, your fingers are in direct contact with the coils. When you pull a wagon, the handle touches your hand. When a football player kicks a ball, the foot makes contact with the leather. Every single one of these interactions requires objects touching each other. Notice something important here. In each case, you can control both how hard you push or pull and which direction you apply that force. You can hit a tennis ball gently for a drop shot or powerfully for a winner. You can aim it cross-court or down the line. That's because force is what we call a vector quantity. It has both magnitude, how strong, and direction, which way. But here's where it gets really interesting. Not all forces work this way. Right now, as you're watching this, you're being pulled toward the center of the earth by a force that's so constant that you barely notice it. Gravity. But here's the thing that puzzled even Newton himself. Earth is pulling on you, and you're pulling back on Earth, but there's no physical connection between you and the planet's core. How is that possible? This puzzle led to one of the most elegant concepts in physics: field forces. Forces that act across empty space, with no direct contact required. Michael Faraday had a brilliant insight. He said, imagine the sun doesn't directly grab Earth and pull it into orbit. Instead, the sun creates an invisible influence, a field that stretches throughout space. Earth doesn't interact with the sun directly. Earth interacts with this invisible field that the sun creates. It's like the sun is broadcasting a signal throughout the universe, and any object with mass that enters this field feels the gravitational pull. And this leads us to something remarkable. All the fundamental forces in nature, the ones that govern everything from atoms to galaxies, are actually field forces. There are exactly 4 of them, and understanding how they work together is the key to understanding physics itself. We've established that the most fundamental forces are field forces, acting across space without direct contact. Now let's explore these 4 forces that shape everything we experience, starting with the most powerful and working our way down. The strong nuclear force sits at the top. This force has one crucial job: keep the nucleus of every atom from exploding apart. Here's the problem it solves. Inside every atomic nucleus, protons are crammed together, but protons carry positive electric charge, and positive charges repel each other with tremendous force. By all rights, every atomic nucleus should instantly fly apart, but they don't. The strong nuclear force overpowers that electric repulsion, binding protons and neutrons together against incredible odds. However, this force has an extremely short range, about 10 to the negative 15 meters. Step outside the nucleus, and it has zero influence. Next comes the electromagnetic force, and this one you interact with constantly. When you rub a balloon on your hair and it sticks to the wall, that's electromagnetic force. When a magnet picks up iron filings, electromagnetic force. When lightning strikes, electromagnetic force. Here's what makes electromagnetic forces special. Unlike the strong force, they have infinite range. They get weaker with distance, but they never completely disappear. And they can both attract and repel depending on the charges involved. The weak nuclear force operates in radioactive decay and powers the nuclear reactions inside the sun. Like the strong force, it only works at extremely short ranges, but it's much weaker. Finally, gravity, the weakest of the four fundamental forces, yet the one that shapes our daily experience and the large-scale structure of the universe. Here's something that might surprise you. Gravity is so weak that a tiny refrigerator magnet can overpower the gravitational pull of the entire Earth when it picks up a paperclip. But gravity has two crucial advantages. It only attracts, never repels, and it has infinite range. So while it's individually weak, it adds up across vast distances and enormous masses. Now, here's the key insight for everything we experience day to day. In classical physics, you only directly encounter two of these four forces, gravity and electromagnetic forces. The strong and weak nuclear forces are locked away at the atomic level. But every contact force you feel is actually electromagnetic forces in disguise. When you push off the ground while walking, that's electromagnetic forces between electrons in your shoe and electrons in the pavement. When you sit in a chair, electromagnetic forces prevent you from falling through. Here's where forces reveal their full power. They don't just move objects from place to place. Forces also change the shape of objects, and this is crucial for understanding how the world works. When that tennis player hits the ball, watch carefully. The ball doesn't just change direction, it actually deforms. The racket strings compress the ball, squashing it almost flat for a brief moment. Then the ball springs back to its original shape, and that elastic rebound helps launch it across the court. This deformation happens with every force interaction. Even objects we think of as completely rigid actually bend and compress under force. When two cars collide, the metal crumples. When you step on concrete, both your shoe and the pavement deform slightly under your weight. Sometimes these deformations are temporary, like a tennis ball bouncing back. Sometimes they're permanent, like the aftermath of a car crash. But the deformation is always there, reminding us that forces reshape the world around us. Think about what this means. Every contact force you've ever felt involves this dance of deformation and response. Your muscles work by contracting and pulling on your bones. Your bones flex slightly under the load. Buildings sway in the wind. Even the Earth itself deforms as the moon's gravity creates tides. This is the deeper story of forces. They're not just abstract pushes and pulls from your physics textbook. Forces are the universe's way of communicating. They carry information from one object to another. They transfer energy. They create motion and change. That tennis ball from our opening example, catching it involved electromagnetic forces holding every atom in your hand together, gravitational forces pulling the ball toward Earth, contact forces as your palm stopped the ball's motion, and nuclear forces keeping every atom stable throughout the interaction. You're surrounded by this constant conversation of forces, contact forces and field forces working together to create every interaction you experience. From the atomic scale, where nuclear forces bind matter together, to the cosmic scale, where gravity shapes galaxies, forces are writing the story of everything that moves, changes, and exists. And now you understand the language they're speaking.